Step outside on a brisk winter night and catch a single snowflake on your glove. Hold it close to your gaze. 6 arms spread with fractal precision, each branch echoing the next in icy miniature. Rotate the flake 10 degrees, 20, 30. Every turn returns the same silent geometry, as if nature had traced one crystalline stanza and set it spinning through space. We find such balance enchanting because it whispers of order, a suggestion that the universe is composed not merely of things but of rules. Deep, hidden symmetries that choreograph matter and light. In the language of physics, symmetry is far more than decoration. It is a promise. When the laws of nature look identical tomorrow as they did an instant ago, a quiet covenant forms. Energy must be conserved. Slide a laboratory bench a meter to the left and discover the equations stay unchanged. Momentum is guaranteed. Tilt your head beneath the stars, pivot through the darkness, and because the cosmos presents the same face in every direction, angular momentum endures. These invisible guide rails trace back to one mathematician, Emmy Noether, who revealed that every conservation law is the echo of a symmetry in disguise. Yet perfection alone cannot write a story. Imagine a universe with flawless symmetry, no wrinkles of imbalance, no tiny deviations. Stars would not ignite. Fusion requires a loophole in perfect mirror law to let protons slip past their mutual repulsion. Galaxies would never coagulate. Gravity needs initial asymmetric seeds to gather dust into spirals of starlight. Even life, mirrored hands constructing mirrored cells, relies on a cosmic preference. Amino acid spirals, all curl left. Sugars spiral right. Somewhere in the earliest moments after the Big Bang, symmetry cracked just enough to widen possibility without erasing harmony. Across the heavens, these fractures shine. The sun above us balances on a razor's edge of time symmetry. It's converting 4 million tons of mass into light every second, yet never flickering beyond a whisper. Deep within its core, the weak force betrays mirror symmetry, allowing rare interactions that set the stellar furnace to a simmer instead of an explosion. Farther still, in particle colliders beneath the Alps, physicists hunt for vanishing differences. Subtle violations of charge and parity that might explain why we have galaxies instead of a sterile sea of light. Tonight, let us follow the compass of symmetry from the elegance of Noether's theorem through the cosmic kill of starlight. Onward to the purposeful fractures that give the world texture and us a place within it. We will see how symmetry shields energy, how breaking it gifts mass, how the slightest tilt of a universal mirror chose matter over antimatter, paving the way for galaxies, worlds, and wondering minds. In the balance between order and imperfection lies everything we cherish: the steady glow of morning, the crystalline dance of snow, the heartbeat syncing with the hush of night. Welcome to Symmetry, the code that makes stars burn. Berlin, winter of 1917. Albert Einstein, pockets full of pipe ash and head full of curved space-time, paced the parquet floors of his apartment. He had bent gravity into geometry. Planets orbited because valleys in space guided them, but a quiet arithmetic haunted him. In Newton's universe, energy moved from one ledger to another with immaculate clarity. In Einstein's, the books came up fuzzy. Shift your coordinates. The energy stored in a gravitational field seemed to leak away or reappear like a conjurer's coin. Down the rail line in Göttingen, mathematician David Hilbert sensed the same discomfort. He could wrangle tensors as deftly as any physicist, yet the balance sheet refused closure. So he turned to a colleague who, until then, lectured in borrowed classrooms because women were barred from professorships. Emmy Noether. Where others saw equations, Noether saw underlying harmonies, structural chords that persisted when variables flexed. Hilbert presented the energy riddle. She retreated behind chalk-dusted doors. Months later, she resurfaced with an answer so distilled it felt inevitable. If a physical system's equations remain unchanged, invariant, under a continuous transformation, then some measurable quantity must stay constant. Noether had not merely patched Einstein's bookkeeping. She had revealed the very mint that prints nature's conserved coins. The geometry of gravity, the glide of an electron, the spin of a galaxy, all would now be judged by their hidden symmetries. Translate a pendulum experiment forward 1 millisecond. The laws guiding its swing do not blink. That almost trivial statement that physics is indifferent to the tick of the clock locks in the conservation of energy. Slide the entire laboratory a meter east. With no preferred origin, momentum must balance eternally. Rotate the apparatus under the ceiling lamp. Because the equations care nothing for orientation, angular momentum spins on inviolate. This is Noether's theorem in its purest breath. Symmetry births conservation. The proof runs through the Lagrangian formalism, but its soul is simpler. Continuous symmetries, meaning smooth changes you can dial from zero to a whisper. Forge currents, quantities that neither appear from nowhere nor vanish into the void. An unchanging timeline yields an energy current. A featureless landscape yields momentum. A directionless cosmos yields angular momentum. Every polished gem of invariance casts a shadow that we measure in laboratories and feel in our bones. Even abstract forces obey. The electroweak field stays invariant when its quantum phase rotates. So, electric charge cannot be created or destroyed. Quantum chromodynamics respects color-3 symmetry, binding quarks under an unbreakable book balance of color charge. With a single stroke of chalk, Noether transformed bookkeeping from empirical habit into mathematical destiny. In the chapters that follow, these invisible currencies will pay the bills of the cosmos powering fusion in the sun, deciding why matter outweighs antimatter, and reminding us that every flicker of starlight is the dividend of a symmetry honored since the first moment time had meaning. Look up at midday. The sun pulses 150 million kilometers away, yet its brilliance scarcely wavers, never flaring hard enough to scorch oceans, never dimming enough to freeze continents. A constancy is no happy accident. It is the direct consequence of Noether's most familiar symmetry, the sameness of time. In the furnace at the sun's core, 4 protons combine to form a helium nucleus. To positrons, to neutrinos, and pure radiance. Because the equations governing that reaction remain identical from one heartbeat of the universe to the next. The bookkeeping of energy must balance with diamond precision. Every photon streaming through your window is paired with a fractional loss of mass inside the star. An exchange so precise that after 5 billion years, the sun's brightness has crept upward by only a third. Translation symmetry joins the vigil. Deep inside, pressure battles gravity, layer on layer. If space favored one location over another, momentum could bleed sideways, collapsing equilibrium. But momentum is conserved because space itself refuses bias. Therefore, the outward push of photon pressure matches the inward pull of weight everywhere, from equator to pole. Even tiny acoustic oscillations, helioseismic waves, reveal a star balanced by invisible Noether currents. Their rhythms confirming the sun's structure 2 parts per million. Symmetry does not merely describe the star, it keeps the light on, frame by frame, day after irreplaceable day. With Noether's ledger in hand, scientists learned to hunt the unseen. In 1919, during a total eclipse on the coast of Principe, Arthur Eddington measured starlight deflected by the sun. Energy momentum conservation carried along null geodesics of curved spacetime. Predicted exactly the bending Einstein had dared to publish. The match crowned relativity, but the method was Noetherian. Trust the conserved current and test the geometry around it. Decades later, nuclear reactors puzzled researchers with missing beta decay energy. To preserve energy conservation, Wolfgang Pauli proposed an invisible lepton, the neutrino. 26 years on, Clyde Cowan and Frederick Rains caught neutrinos in a tank of water and cadmium chloride, vindicating Pauli and Noether at once. Particle colliders repeat the ritual daily. When quarks collide inside the Large Hadron Collider, detectors reconstruct spray patterns. Any imbalance in momentum or charge triggers alarms, either a detector glitch or a portal to new physics. Dark photons, supersymmetric partners, perhaps hints of hidden symmetries, still uncharted. Even the discovery of the Higgs boson hinged on closing an energy gap in decay products, assuring Noether's book's balance to the last electron volt. Across astrophysics, nuclear physics, and quantum field theory, conservation laws act like forensic lamps, illuminating invisible actors, exposing theoretical forgeries, and guiding explorers toward deeper layers of symmetry yet to be revealed. Physicists are magpies for elegance. Dirac once said an equation's beauty could outrank experimental proof, and history often rewarded that faith. Maxwell's perfectly symmetrical scroll fused electricity with magnetism. Einstein's field equations, spare as calligraphy, predicted black holes in an expanding cosmos. Time and again, symmetry has lit the path before evidence arrived. But a good compass can still mislead. For 40 years, theorists pursued supersymmetry, the notion that every fermion partners with a mirrored boson, racing quantum infinities in a mathematically pristine dance. Collider after collider probed deeper, yet no superpartners appeared. The universe, it seems, is willing to bend aesthetic rules if another subtler symmetry, or an exquisite asymmetry, better serves its story. The lesson is humbling. Symmetry is guidance, not gospel. It tells us where to look, which quantities to count, how to guess the next verse in nature's poem, but it does not guarantee the rhyme. When data disagree, elegance must yield. History's most creative moments emerge where perfect balance cracks. The lopsided decay of kaons, the tiny mass differences that let neutrinos oscillate, the electroweak symmetry broken by the Higgs field so particles could gain heft. Beauty still matters. It whispers the language of the deep. But it is the dialogue between symmetry and its fractures that writes the cosmos we inhabit. Gaze again at the midday star. Its brilliance is a paradox of precision and imperfection. Time symmetry keeps the energy books balanced, yet something else, a deliberate crack in mirror law, must tip the odds so protons confuse in spite of their mutual repulsion. Without that loophole, the sun would hoard its hydrogen in frigid silence. Too large a loophole, and it would erupt in a fatal flash. In Part 2, Symmetry ignites the sun. We will plunge into that nuclear courtroom. We will watch quantum tunneling sneak past perfect electrostatic symmetry and see the feeble, left-handed nature of the weak force slow the fusion rate to a life-friendly simmer. From there, we will trace how symmetry and its nuanced violations shaped every photon warming your skin. Every aurora that dances at Earth's poles, every heartbeat timed by the rise of dawn. The journey ahead is not merely stellar, it is personal. The warmth that ripens fruit and steadies climates is the direct consequence of nature's willingness to keep her deepest symmetries, yet bend them just enough to let stars breathe. Let us step into the furnace and witness that delicate compromise in action. Descend by thought experiment to the sun's core. Hydrogen nuclei jostle in a sea of 10 million degree plasma, each a bare proton cloaked only in positive charge. Bring two protons close and electrostatic symmetry rears like an iron gate, like charges repel with a force that climbs as distance falls. At a separation of a trillionth of a meter, the repulsion towers to more than 1 million electron volts, far above the average kinetic energy in the stellar furnace. Classical physics rules. The gate is locked, fusion should freeze, and the sun should sit dark and celestial cold. Yet outside your window, daylight spills with effortless patience. Something is breaching that perfect symmetry, slipping protons past the Coulomb wall thousands of trillions of times each second. Classical trajectories fail, so we turn to the quantum view. Every proton is also a wave, its edges smearing into forbidden territory. Where particles bounce, waves leak. Like muffled sound through a thick wall, a sliver of probability seeps under the barrier, hinting that the gate may not be absolute after all. The question becomes, not if protons can cheat the repulsive law, but how often. Answering it calls for a dance of wave functions and an exponential law named for a Russian emigre. Our next step toward understanding how our sun learned to burn. Entered George Gamow, who saw beyond marbles and walls to probability clouds. He calculated that a proton's wave function doesn't halt at the Coulomb peak. It thins, but penetrates, a phenomenon we now call quantum tunneling. The likelihood of emergence on the other side decays exponentially with barrier height and width, coded in the elegant Gamow factor. Inside the sun, thermal collisions jostle proton waves against the wall billions of times per second. Most rebound. Yet the high-energy tail of the Maxwell-Boltzmann distribution provides a rare cadre of swift particles. The elite climbers of this electrostatic Everest blend that energetic tail with Gamo's tunneling odds, and you find a sweet spot. The Gamo peak, where collision energy and barrier transparency conspire to make fusion just probable enough. Astonishingly, that sweet spot is tuned so delicately that an average proton waits 10 billion years before it fuses, a timescale that grants Earth eons for oceans, trilobites, and language. Where the peak shifted a little higher, the sun would gutter cold, a hair lower, and it would detonate in a ferocious flash. Thus, quantum tunneling acts as nature's backdoor, respecting the global symmetry of charge repulsion while exploiting its quantum loophole. The gate remains, the law unbroken, yet life-giving fire slips quietly through the cracks. In the next scene, we'll meet an even subtler asymmetry, a weak interaction that nudges tunneling protons into deuterium and lights the stellar fuse. Quantum tunneling alone brings two protons nose to nose, but symmetry still bars fusion. Identical charges, identical flavors, no way to bind. Salvation arrives from the most retiring of nature's interactions, the weak force. Unlike its strong and electromagnetic cousins, the weak interaction flaunts a tiny imperfection. It violates mirror symmetry. In its domain, left and right are not interchangeable. Left-handed particles dance, right-handed partners sit out. When two protons tunnel close enough, one can slip through this asymmetric loophole. By emitting a positron and a left-handed neutrino, the proton flips into a neutron, and the pair locks together as deuterium. This beta transmutation is breathtakingly rare. On average, a proton waits the age of Earth's oceans to experience it. But the Sun hosts 10 to the power 38 opportunities every second. Those few successes cascade. Deuterium fuses with another proton to form helium-3. To helium-3 nuclei merge into helium-4. And a flood of photons begins a 200,000-year random walk to the surface. Because the weak force is, well, weak, the star burns with serene longevity. Strengthen that interaction, and solar lifetimes would shrink to mere millions of years. Weaken it further, and fusion might never ignite. The sun's gentle blaze is a testament to the power of imperfection. How a slight skew in mirror law turns tunneling whispers into the roar that lights our days. Every weak force, alchemy issues two invisible tickets: a left-handed neutrino and a positron. Positrons annihilate almost at once, adding to the photon tide. Neutrinos, nearly massless and indifferent to charge, flee the solar core at close to light speed, ghosting through convective layers, photosphere, planets, people, in the time it takes you to read this sentence. About 100 trillion solar neutrinos will have passed through your body, leaving no trace. Yet trace them, we have. In the 1960s, Raymond Davis Jr. buried a tank of dry-cleaning fluid deep under South Dakota rock. A handful of argon atoms appeared each month, chlorine nuclei transmuted by solar neutrinos, notarizing the proton-proton chain. For decades, the count was mysteriously low. The deficit hinted at new physics. And indeed, the neutrinos themselves carried another subtle symmetry surprise. They oscillate, morphing between electron, muon, and tau flavors as they fly. Flavor symmetry is slightly broken by tiny neutrino masses. That breakage solved the solar neutrino problem and earned a Nobel Prize in 2015. Today, water Cherenkov detectors like Super Kamiokande and ribbon phototubes in Antarctica's ice sheet catch bursts of blue light when rare neutrino interactions occur. Each flash is a receipt time-stamped 8 minutes after its journey began, proving that the sun's core still honors Noether's ledger every microsecond. In those ghostly particles, we hold the only direct witness of fusion's first act. A nightly reminder that symmetry's smallest breaches keep the stellar furnace glowing and life's narrative alive. The missing neutrino riddle lingered for 30 years, and like every good mystery, cracked open a deeper law. If electron-flavored neutrinos were vanishing, where did they go? They answered, they never disappeared. They changed costumes in flight. Inside the sun's dense plasma, neutrinos pass through a matter field that nudges their quantum phases differently, an effect known as the MSW resonance. As they escape into vacuum, These phases interfere, rotating the state vector among electron, muon, and tau flavors. Flavor symmetry would keep the three identities locked in perfect balance. All neutrinos were massless, but a sliver of mass less than a millionth of an electron tilts the symmetry, allowing oscillations. Sudbury Neutrino Observatory's heavy water tank finally tallied the full head count. Total neutrino number matched solar model predictions when all flavors were included. The bookkeeping was intact. The universe had simply chosen a subtle break in flavor symmetry to reveal another layer of its code. Those oscillations hint at still hidden symmetries. If neutrinos are their own antiparticles, lepton number could break at energies beyond our colliders, seeding matter over antimatter in the early cosmos. Thus, a shortfall in chlorine counts led physicists from solar fusion to the frontiers of cosmic evolution. Proof again that symmetry's smallest tremor can rattle the pillars of existence. A photon born in the core begins life as a gamma-ray bullet, yet moves through plasma thicker than lead. Momentum conservation locks each scattering angle to the previous, turning the photon's path into a drunken random walk. Billions of ricochets later, 200,000 years on average, it emerges at the photosphere, downgraded to visible light. Conservation laws guide every exchange. Energy bleeds from radiation to plasma, but never vanishes. Momentum shuffles from photon to ion, maintaining hydrostatic balance that holds the star in near-perfect sphere. Beyond the photosphere, magnetic symmetry and its sudden breaks sculpts towering loops that heat the corona to 1,000,000 degrees. Here, alphon waves and reconnection tap conserved magnetic helicity, directing it skyward in solar wind streams that buffet Earth's magnetosphere. 8 minutes after leaving the surface, photons strike ocean waves and leaf canopies, closing a journey that began before humans mastered fire. The sun's light, then, is a palimpsest. First written by quantum tunneling and weak asymmetry, revised by millions of scatterings that honor energy-momentum symmetry, and finally signed by magnetic topology in the corona. Every dawn you witness is both a newborn event and a fossil from a time when continents sat in different places and life had yet to try walking on land. We have seen how a flawless electrostatic rule is bypassed by quantum tunneling, and how an almost negligible mirror symmetry crack in the weak force sets the stellar tempo. Tiny imperfections, balanced against grand invariance, light the sky and lace Earth with neutrino rain. But symmetry's creative power extends far beyond the sun. In the primordial universe, phase transitions shattered once perfect forces, freezing out the Higgs field and scattering seeds that gravity would later sculpt into galaxies. The same physics that lets protons fuse carved the pathways by which matter gained mass and antimatter faded. In Part 3, Broken Symmetry, New Worlds, we'll exit the solar core and roll time back to that incandescent beginning. We will watch symmetry crumble in stages, electroweak, strong, and perhaps supersymmetric, and see how each fracture unlocked new particles, new forces, new possibilities. From the Higgs field's silent choice of direction to the whispered in asymmetry that left us a universe of matter. Imperfection is not an error, it is the architect of everything complex, diverse, and alive. Roll time backward until numbers lose meaning, temperatures trillions of degrees, densities that fold light itself. In that embryonic flicker, the universe knew no distinctions. Forces we separate into gravity, electromagnetism, and the nuclear siblings merged into one super-interaction. Quarks, leptons, gauge bosons. Every particle was a massless note in the same blinding chord. Identities erased by heat. Physicists call this epoch grand unification. In particle accelerators, we see hints. The running strengths of the strong, weak, and electromagnetic forces nearly converge if we extrapolate to energies around 10 to the power 25 electron volts. Beyond that summit, their mathematics may fuse. Described by elegant groups like SU5 or SO10, glimpses remain speculative. But cosmology agrees on the texture. A perfectly symmetric field filling space, smooth as still water, yet storing stupendous potential. The symmetry that complete is fragile, supercooled metal ready to crystallize. The early cosmos awaited the slightest imperfection to shatter its uniformity. Quantum fluctuations, tiny foam-like wiggles, were already whispering beneath the glare, preparing cracks that would let structure bloom. The stage was set. One decisive drop in temperature, and the universe would never be the same again. At 10 trillionths of a second, cosmic temperature dipped below a critical 10 to power 15 Kelvin, and the smooth field that once unified electromagnetism and the weak force wavered. Picture a perfectly round tabletop with a shallow ridge encircling its edge, the Higgs potential. While the universe blazed above the ridge, everything remained centered. Cooling nudged the field. Like a marble on that table, it rolled off the peak and settled into the circular valley. One moment of off-balance and symmetry snapped. This simple displacement rewrote reality. The photon stayed massless, free to roam as light. Its cousins, the W positive, W negative, and Z bosons, suddenly shouldered nearly 100 proton masses. Their range compressed to the heart of the atom, defining the weak force's feebleness. Quarks, previously weightless, gained heft proportional to how tightly they coupled to the Higgs field. Electrons followed suit. Mass, once an abstract potential, crystallized into measurable inertia. Laboratory echoes of that snap appear whenever a Higgs boson materializes at CERN, living for a tiny fraction of a second before decaying in sprays of bottom quarks or photons. Brief reminders of the moment the universe chose a direction in an otherwise featureless field space. Without that tilt, atoms would never bind, stars would never fuse. And Symmetry's perfect hymn would have remained beautiful, yet mute, offering no stage for chemistry, planets, or wondering minds. Microseconds ticked. The universe cooled to 2 trillion Kelvin, and a second symmetry yielded. The strong force, quantum chromodynamics, once let quarks flit freely in a glowing quark-gluon plasma. But as temperature dropped, chirosymmetry fractured, and the color field tightened like an elastic net. The high-energy freedom of quarks gave way to confinement. Flux tubes of color snapped them into permanent triplets and pairs. Out of that lockdown emerged the first permanent matter, protons and neutrons. Burdened now with most of their mass not from quark heft, but from the kinetic frenzy caged within. A sea of lightweight pions, born as the Symmetry's Nambogold stone messengers, who flooded space and quickly decayed, leaving behind an inventory of hadrons that would later assemble into nuclei, stars, and storytelling brains. Today, heavy-ion colliders, like RHIC and the LHC's Alice detector, recreate droplets of that newborn plasma. Sensors record jets of hadrons spraying from collisions. Each jet evidenced the confinement reasserted itself less than a yoctosecond after liberation. In those collisions, we read a fossil memory of the cosmic kill confirming that mass, and ultimately the solidity of mountains, rose not from quarks themselves, but from the broken symmetry of gluon fields freezing into color-neutral knots. Even earlier another field, the inflaton, hovered at the crest of a nearly symmetrical plateau. For reasons we still puzzle over, that plateau was almost, but not perfectly, flat. The slight downward tilt set off inflation. Space-time, expanded by a factor greater than the atomic radius ballooning to the size of the Milky Way, all in a breath of cosmic time. Like a flawlessly still lake suddenly whipped by wind, quantum fluctuations on microscopic scales stretched into macroscopic ripples. Inflation solved riddles that once taunted cosmology. Why is the universe so smooth across regions that never shared light? Because those regions were once neighbors, before inflation yanked them apart. Why is space so flat, sitting at critical density? Because any curvature was ironed out, the way a balloon's surface flattens as it inflates. Eventually the field rolled off its plateau, symmetry breaking again as inflation halted. The inflaton's potential energy transmuted into a hot bath of particles, reheating the universe and setting the stage for electroweak symmetry breaking, and later the QCD freeze. The density ripples, frozen quantum whispers, became the seeds of galaxies etched as temperature freckles in the cosmic microwave background. Modern telescopes, like the South Pole's Bicep Array, sift that microwave light for the faint curl of primordial gravitational waves, a signature of symmetry almost kept, then spectacularly broken to forge the large-scale architecture of everything we see tonight. When the cooling cosmos reached 1 trillion degrees, matter and antimatter should have annihilated in a final, perfect flash, leaving nothing but stray photons. Instead, for every billion pairs that mutually erased, one lonely proton survived, and every atom in your body descends from that minuscule surplus. What tilted the scales? A conspiracy of broken symmetries, known as baryogenesis. Physicist Andrei Sakharov laid the conditions. You must violate baryon number, disturb thermal equilibrium, and most crucial, break CP symmetry so that reactions favor matter over antimatter. In everyday physics, CP holds with iron grip, but in the weak interaction, it slips. Neutral kaons observed at Brookhaven in 1964 decay into pions, slightly more often in one mirror twin configuration than the other. Later, beam assaults at SLAC and Keck repeated the asymmetry. Tiny, yes, but in the cauldron of the early universe, even a 1 part in a billion bias was enough. One candidate mechanism is leptogenesis. Heavy right-handed neutrinos decay out of equilibrium. Breaking CP and Sphaleron processes trade lepton excess for baryon excess before electroweak symmetry fully freezes. Another possibility lurks in undiscovered particles that skew decay channels just so. Experiments at LHCb and Bell 2 now sift trillions of beam-son decays for anomalies. While neutrino-less double beta studies hunt lepton number violation that could confirm the leptogenesis script. Whatever the agent, the lesson endures. An almost imperceptible fracture in symmetry is stamped on every star, planet, and strand of DNA. A cosmic preference that made something instead of nothing. Symmetry seldom breaks without leaving fingerprints. As the universe cooled through successive phase changes, it risked knitting geological scars into space-time itself. Topological defects. Imagine cooling water into ice. Crystals form with misaligned facets, creating grain boundaries. In the grander cosmic crystal, analogous flaws emerge. A misorientation in a unified field could freeze into a magnetic monopole, a north pole without a south. A scalar field choosing left while its neighbor chooses right traps a domain wall, a vast membrane of trapped energy. Lines where field phases misaligned can freeze into cosmic strings. Ultrathin filaments denser than neutron stars and stretching across galaxies. Inflation likely diluted most defects, but not necessarily all. Modern radio surveys and pulsar timing, arrays scan for the rhythmic shiver of gravitational waves that vibrating cosmic strings would emit. The recent nanograv signal a low-frequency hum teases at such relics. Though astrophysical explanations vie for the podium, future detectors, LIGO Voyager, and the spaceborne LISA antenna may resolve the spectrum and decide. Even if strings hide, their mathematics guides condensed matter labs, vortices and superfluid helium, flux tubes in Type II superconductors, and skymions in magnetic lattice all map onto cosmic string equations. The universe, it seems, practices its grand designs on every scale from tabletop cryostats to intergalactic webbing. Each scar a reminder that perfect symmetry, once broken, never quite heals without a trace. Today's physicists comb the cosmic attic for leftover clues of those symmetry-shattering moments. Down a 700-meter shaft in South Dakota, the Lux Zeppelin detector waits for a dark matter particle to nudge its vat of liquid xenon. Testing theories that add hidden dark symmetries to the standard model. Under the French-Swiss border, CERN's LHCb counts the decays of beauty mesons, checking whether matter still favors itself over antimatter by a hair more than the textbooks allow. Elsewhere, ultra-cold neutrons linger in magnetic bottles, while researchers measure their electric dipole moment. Even a shift smaller than 10⁻⁻28 would expose a fresh violation of CP symmetry, and perhaps the mechanism that set the primordial matter surplus. Radio telescopes join the chase. The CHIME and HIRAX arrays monitor fast radio bursts whose dispersion patterns could imprint interactions with axion-like particles. Hypothetical remnants of a symmetry broken so softly we have never heard its whisper. Gravitational wave observatories, too, now double as symmetry sleuths. A network of Earth-sized pulsar timing baselines listens for nanohertz ripples that tangled cosmic strings would release. While LIGO Voyager's cryogenic mirrors will probe the kilohertz band for echoes of hidden sector phase transitions, each non-detection sharpens theory's focus. Each anomaly hints the universe still keeps secrets stitched in broken patterns waiting to be read. Imagine if symmetry had remained flawless. Photons would sail unimpeded through a sea of massless quarks and leptons. No atoms, no chemistry, no color. It is the missteps that give the universe texture. The Higgs field's tilt grants particles inertia, allowing electrons to orbit nuclei instead of racing off at light speed. The QCD freeze locks quarks into protons and neutrons, whose slight mass difference lets the neutron decay. Freeing energy that powers stellar alchemy, further asymmetry arranges electrons into shells, carving the periodic table staircase. Sodium flares in street lamps. Copper conducts music to headphones. Iodine guides hormones. All because a symmetric quantum equation bent just enough to let orbitals vary. On grander scales, inflation's stretched fluctuations gather baryonic matter into filaments, birthing galaxies that churn heavier elements in their cores. Those metals seed rocky planets where broken molecular parity chooses left-handed amino acids and right-handed sugars. Tiny prejudices that let enzymes snap together with exquisite specificity. Thus, the cosmos is not merely tolerant of imperfection. It is dependent on it. Symmetry lays the framework. Symmetry colors the canvas, ensuring a sky peppered with galaxies. A table of elements rich with possibility, and a biosphere capable of asking why the balance is so artfully off-center. The universe's deepest dramas played out in fractions of a second, but their signatures echo into every snowflake and sunlit crystal today. The same mathematics that govern the Higgs field shapes water molecules into six-fold stars and arranges carbon into hexagonal graphene sheets strong enough to suspend a cat on the width of a human hair. In Part 4, Beauty, Patterns, and Snowflakes, we will descend from cosmic furnaces to the everyday artistry of symmetry. How translational order in salt yields transparency in halite. A band structure symmetries, let silicon switch your phone's logic. And how life itself exploits chiral preference to build spirals of DNA that archive memory across generations. We leave the roaring early universe and step into a quieter, colder realm where symmetry is no longer shattering but tessellating, assembling snowfields, cathedral arches, and the whorls of a sunflower. The grand laws remain, but now they whisper in ice and petals, reminding us that every breath we take owes gratitude to a cosmos that found its beauty not in perfect mirrors, but in mirrors artfully cracked. Lift a stray snowflake to lamplight and watch a miracle of arithmetic unfold. 6 arms grow in lockstep, each branching at the same 60-degree cadence, each cradling sub-branches that echo the parent form. The secret is water's hydrogen bond. 2 slight positive charges cling to 1 negative oxygen like outstretched hands. Fixing the angle between neighbors at 120 degrees, stack those molecules into solid lattice, and a hexagon appears by geometric inevitability. Yet symmetry alone doesn't birth individuality. As the crystal drifts through turbulent pockets of humidity and temperature, growth speeds vary along its arms. Diffusion-limited deposition accentuates edges, slows recesses, carving fernleaf tracery unique to a single moment in the cloud. A snowflake, then, is a diary of atmospheric whims written on a template of molecular symmetry. 6-fold order supplies the grammar. Micro-instability writes the poetry. Once the flake touches your sleeve, its delicate hierarchy sublimates. But for a heartbeat, you hold evidence that cosmic laws guide even the lightest whisper of winter. Shift your gaze to a grain of table salt under a microscope. You'll find an endless city of cubes. Chloride anions and sodium cations alternating like tiled streets. Slide that lattice 1-unit cell to the right, or upward or into the page, and the scenery repeats without change. This invariance under translation forms the heartbeat of crystallography. In 1912, Max von Loewe pierced zinc blende with X-rays. The scattered beams converged into a speckled constellation on photographic film. The lattice imprint in reciprocal space, von Loewe's pattern, decoded atomic positioning more precisely than any ruler could measure. Today, synchrotron rings achieve the same feat in microseconds, revealing new polymorphs for catalysts and battery electrodes. All rely on symmetry's clarity. When the arrangement repeats perfectly, waves interfere constructively along specific angles, broadcasting the crystal's internal poem to the outside world. But perfect periodicity does not forbid creativity. Quartz twists its helices, calcite splits light in perovskites fold octahedra. Each variation, a different verse within translational meter. Like music constrained by time signature yet free in melody, crystalline matter translates symmetry into endless functional motifs. From strengthened diamond to piezoelectric song and sonar ceramics, slide deeper, and electrons themselves become poets in a periodic landscape. In free space, an electron may adopt any wavelength. Inside a crystal, its wave function must harmonize with lattice spacing. According to Bloch's theorem, allowed energies cluster into bands separated by forbidden valleys, band gaps. These gaps are not arbitrary. They arise because electron waves reflecting off repeating ions can interfere destructively, much as noise-canceling headphones. Quiet a steady hum. Silicon, arranged in diamond cubic symmetry, hosts a gap of 1.1 electron volts, wide enough that at room temperature electrons sit quietly in the valence band, yet small enough that a trace of phosphorus can tip them into conduction with modest voltage. Pion junctions, solar cells. And every logic transistor on Earth function because this gap is neither too wide nor too narrow, but exquisitely just so. Alter the symmetry, compress silicon, alloy it with germanium, twist it into 2D sheets, and the gap shifts, tailoring infrared detectors or high-speed lasers. Thus, the smartphone in your pocket is a triumph of symmetry engineering. It converts bits to music, maps, and memory by choreographing electrons across structural repeats measured in angstroms. The next time you tap a glass screen, remember, the click of information begins in the silent rhyme scheme of silicon's crystal lattice, patterns solid yet invisible. Born from the same geometric insistence that sculpts every snowflake drifting beyond your window. Peel a single layer from pencil graphite, and you reveal graphene. A sheet 1 atom thick, stitched into a honeycomb so faultless that engineers call it two-dimensional, which carbon bonds to 3 neighbors at 120 degrees, repeating a hexagon across kilometers of potential film. In that symmetry, electrons forget they have mass. Their energy momentum curve sharpens to Dirac cones. Twin funnels that meet at a point where charge carriers sprint at 1/300th the speed of light. Twist one graphene sheet atop another by a magic 1.1 degrees and more patterns emerge, enlarging the unit cell 1,000-fold. The symmetry softens, the Dirac cones flatten, electrons slow to a crawl and, almost lazily, pair into superconducting states at temperatures once thought impossible for carbon. Valley symmetry, once trivial, becomes a quantum label engineers can tweak with gentle strain. Birthing valletronics where information might flow, not by charge but by which side of a Dirac cone an electron occupies. Thus graphene is a paradoxical gift. Symmetry so perfect, it grants particles near relativistic freedom, yet flexible enough that a mere twist spawns new phases of matter. A mundane pencil stroke hides a playground where geometry dictates not only form, but future technologies. Transparent circuits, quantum sensors, perhaps even room temperature, superconductors waiting in the angles between hexagons. Hold your palms together, identical outlines, yet mirror images that refuse to overlap. Molecules share this handedness in life for reasons still debated, chose sides. Every amino acid in your muscles and neurons twists to the left, every sugar in your DNA spirals right. Flip the orientation, and enzymes stall. Receptors misfire, metabolism grinds to a halt. How did biology pick its favorite glove? One clue lies in meteorites such as the Murchison Fall, where the amino acid serine appears in a left-handed excess. Perhaps circularly polarized ultraviolet light, filtered through star-forming clouds, destroyed right-hand molecules more readily, seeding Earth with a modest bias. Autocatalytic chemistry could then amplify that 1% lead into total dominance, like a single snowball, triggering an avalanche. Physics whispers an even subtler hint. The weak force violates mirror symmetry. In beta decay, electrons emerge preferentially left-handed, imbuing space with a minuscule chirality. Calculations show the resulting energy difference between left and right-hand amino acids is far too small to drive selection directly, but enough, perhaps, to tip a cosmic coin when chemistry teetered on the edge. Whatever the origin, homochirality makes biology possible. Proteins fold because identical hands clasp in predictable ways. DNA zips because sugars twist uniformly. The next time a heartbeat echoes in your chest, remember it is orchestrated by a left-handed. Bias written not only in cells but in the breaking of a universal mirror eons before the first spark of life. Symmetry can also break in real time, weaving living tapestries from simple rules. In 1952, Alan Turing, better known for code breaking, posed that two reacting chemicals diffusing at different speeds could paint stripes, spots, or spirals on an otherwise featureless sheet. Today we watch reaction diffusion waves roll across Petri dishes, cobalt blues blooming into rings of yellow and splitting into leopard-like rosettes, mathematics written in pigment. Look skyward at cumulus clouds boiling above a hot plain. The hexagonal cells of rising air are a Rayleigh-Benard convection pattern. Asymmetry under vertical translation shatters when temperature gradient exceeds a critical value, forcing orderly rolls to channel the heat. On a grander canvas, Jupiter's Great Red Spot and the spiral arms of galaxies follow similar hydrodynamic equations. Proof that instability can sculpt structures across 80 orders of magnitude. Even your own skin bears Turing's signature. Zebra bands, leopard rosettes, the whirl of a fingertip. All trace back to molecular gradients that broke uniformity in the embryo. Tiny asymmetries at a cellular scale balloon into macroscopic identity. The difference between a tabby stripes and a cheetah spots is the ratio of diffusion constants for two proteins. Thus, from laboratory beakers to planetary storms, patterns emerge not by blueprint, but by symmetry that can no longer hold. Blossoming into order as beautiful as it is inevitable, echoing the cosmic fractures that once seeded galaxies, now replayed in every raindrop swirl and seashell spiral. In 1982, Don Schechtman cooled an aluminium manganese alloy and aimed an electron beam through the newly formed grains. The diffraction pattern that bloomed on his screen carried tenfold symmetry-sharp spots, arranged in rings like a celestial mandala. Classical crystallography declared the image impossible. True crystals repeat at regular intervals. Such repetition forbids 5, 8, or 10-fold rotational orders. Yet the pattern was unmistakable. The alloy was a quasicrystal ordered, but not periodic. Its atoms occupy a mathematical tiling, akin to Penrose patterns. Two rhombuses, in ratios of the golden mean, filling space without ever repeating. Walk the atomic arrangement, and you never meet the same environment twice. Yet long-range order persists, reflected in those sharp diffraction peaks. Quasicrystals blur lines between solid and art. Their periodic order yields low thermal conductivity and unusual surface friction. Today, they harden non-stick cookware, reinforce steel gears, and inspire architects who weave Penrose tilings into glass facades. Forbidden symmetry, once dismissed as error, now stands as proof that nature's vocabulary extends beyond perfect repetition, speaking fluently in patterns that are ordered but forever new. Hold a sprig of Romanesco broccoli. Each turret mimics the whole vegetable, spiraling in golden ratio whirls that repeat across scales. Such fractals arise when symmetry is broken, not in space but in size. Zoom into a river delta, a lightning strike, or the alveoli of a lung, and the branching geometry echoes itself. An iterative mantra marching toward invisibly fine detail. Benoit Mandelbrot gave these shapes their name and the mathematics to describe them. Feed a simple complex number equation through endless feedback and the now iconic Mandelbrot set appears: coastlines, spirals, dendrites, nested within one black heart. The fractal dimension, a non-integer measure between line and plane, quantifies how rugged a form remains as you zoom. Coastlines lengthen, clouds gain area. Networks of neurons pack immense surface into small volumes, optimizing diffusion of nutrients or thoughts. Fractals teach engineers, antennas patterned on the Sierpinski gasket resonate on many frequencies. Fracture analysis of metals uses self-similar crack fronts. Computer graphics compress mountains and coastlines with recursive algorithms. Symmetry in scale does not show as harmony, but as boundless complexity and ode to imperfection repeated again and again. Why do humans find symmetry soothing? Neuroscience suggests our visual cortex fires more efficiently when patterns mirror or repeat. Less metabolic fuel is spent predicting the next curve. Yet perfect regularity becomes boring. Music stuck on a single chord. Architecture locked in sterile grid. Artists and architects instinctively insert broken symmetry. A jazz syncopation. The staggered facati of Gaudi's Casabatlo. The off-center pupil in a Renaissance portrait that breathes life into marble calm. Evolution exploits the same sweet spot. A peacock's tail is broadly symmetric, signaling genetic health. But each feather's micro-pattern deviates just enough to prove it is real, not parasite, distorted mimicry. Flowers advertise nectar with radial balance that guides bees, yet slight petal irregularities distinguish one species from another, steering pollination fidelity. Thus, our sense of beauty is a dialogue with symmetry, not a worship. We crave the familiar rhythm so our brains may rest, then the unexpected twist so curiosity wakes. In snowflakes, crystals, even Lombardi spiraled galaxies, nature composes that aesthetic innately, inviting us to resonate with patterns that whisper both order and organic surprise. Imagine a universe reflected in a flawless mirror. Electric charges would flip, but forces should behave identically. A left-handed neutrino becomes right-handed. Clockwise decay unwinds counterclockwise. Physicists give names to these reflections. C changes particles to antiparticles. P reverses left and right. Test them together. CP symmetry and reason suggest nature ought to stay impartial. But peer into the subatomic theater of the weak interaction, and the mirror cracks. Beta decay, for example, throws electrons preferentially in the opposite direction to a nucleus's spin. Always to the left of motion, never to the right. This handedness is baked into the mathematics. Only left-handed neutrinos and right-handed antineutrinos participate. Swap charge and parity, and the weak force does not recognize its own reflection. The betrayal is tiny in everyday life, yet profound in implication. If mirrors can lie at the quantum scale, then matter and antimatter need not balance exactly. This bias, subtle as a misplaced footnote, creates a loophole in conservation stories told since Noether. Matter can emerge with a hair's advantage, provided the rules bend just enough at pivotal moments. Identifying where and how those bends occur is more than academic. It answers why the night sky shines with galaxies instead of a uniform haze of annihilation light. Enter the humble kaon, a meson built from a strange quark and a down antiquark. In 1964, at Brookhaven National Laboratory, James Cronin and Val Fitch fired neutral kaons through a beamline designed to isolate those that normally lived longer. Particles expected to decay only into 3 pions, a C-pure specting mode. To their astonishment, some of these long-lived kaons decayed into 2 pions, a channel forbidden if CP symmetry were absolute. The result was minute. Roughly 1 in 500 decays broke the mirror, but minute was enough. That sliver of excess could, in the furnace of the early universe, snowball into the 1 in billion matter surplus that outlived mutual annihilation. Cronin and Fitch's bubble chamber photographs. Delicate curls frozen in liquid hydrogen were the first direct evidence that CP symmetry could fail. Follow-up experiments deepened the rift. CERN's NA48 and Fermilab's KTeV refined the asymmetry. Today, Japan's Bell 2 and CERN's LHCb extend the hunt to heavier B mesons, where the standard model predicts even larger CP cracks. Each dataset narrows possibilities for new physics. Unseen heavy quarks, exotic Higgs cousins, or lepton number tricks tied to neutrino masses. The kaon's quiet treachery taught cosmology a vital lesson. Cosmic balance can pivot on an almost invisible preference. The quest now is to measure that preference everywhere it might hide, until the arithmetic of existence adds up without hand-waving, leaving us either satisfied or staring at a doorway to forces still unnamed. At CERN's LHCb and Japan's Bell to experiment, colliding protons and electrons birth torrents of B mesons containing bottom quarks. These mesons oscillate between matter and antimatter forms, much like kaons, but their heavier mass amplifies the weak force's complex phase, making CP-violating effects easier to spot. Physicists sift through quadrillions of decays, comparing how often a B meson becomes a kaon plus pions versus how often its antimatter twin does. Angular distributions, decay times, and charge imbalances. all paint the same picture. The mirror still lies. And the lying follows patterns predicted, yet not fully exhausted by the standard model. Intriguing tensions appear in rare transitions. If confirmed, they may hint at undiscovered particles carrying their own symmetry quirks. Meanwhile, tabletop experiments chase CP cracks in different arenas. Ultra-cold neutron traps probe the neutron's electric dipole moment. Atomic clock comparisons test whether fundamental constants drift with Earth's motion through the cosmos. Each negative result narrows theory. Any positive signal could rewrite cosmology overnight. The quest is both forensic and prophetic. Measure the weakest biases in quark decays, and you may decode how a 1,000,000,000-to-1 preference in the early universe blossomed into every galaxy shining tonight. Long before data arrived, Andrei Sakharov drafted a recipe for cosmic imbalance. First, baryon number must be violated. Processes must occasionally turn quarks into leptons or radiation. Second, C and CP symmetry must break, so matter-favoring reactions marginally outpace their antimatter twins. Third, these reactions must occur out of thermal equilibrium. Otherwise, forward and reverse processes cancel the gains. Several theoretical kitchens try to cook the universe's surplus. Lectoweak baryogenesis uses high-temperature fluctuations of Higgs and gauge. Fields Fullerens to violate baryon number, while CP violating phases in the Higgs sector tip the odds. The scenario demands extra Higgs-like particles. LHC has yet to taste them. Leptogenesis begins with heavy right-handed neutrinos decaying asymmetrically. Then lets Fullerens convert lepton excess into baryon excess. Upcoming neutrino mass measurements and neutrinoless double beta decay hunts may confirm or close that kitchen. Whatever the mechanism, the numbers are stark. For each billion annihilations, one lonely baryon slipped through, carrying with it all future stars, planets, and possibilities. The tiniest fissure in CP symmetry thus acts like a cosmic seed crystal. It's imperceptible in isolation, but decisive when multiplied by the furnace of the Big Bang. In the next part, we venture beyond kaons and bimesons to explore hidden symmetries that might still wait in the shadows. Promising answers are deeper mysteries about why reality chose something over nothing. Picture the newborn cosmos as a vast ballroom where matter and antimatter waltz in perfect pairs. Each step is mirrored, every twirl matched by its inverse until, somewhere in the choreography, the mirror cracks. Out of 1,000,000,000 couples, a single proton misses its antiparticle partner. That survivor, and others like it, seed every star now lighting the sky. The margin is ludicrously thin, a baryon-photon ratio. Yet the cosmic microwave background, glowing at 2.7 Kelvin, confirms it. Those relic photons outnumber protons by the same factor everywhere astronomers point their antennas. The surplus traces back to CP-violating decays in the universe's first instance. Perhaps heavy right-handed neutrinos that split into leptons ever so slightly more often than antileptons. Electroweak's Fullerens then rewrote that lepton bias into a baryon surplus, locking protons and neutrons into the future. Today, each sunset, every breath, and the iron in a compass needle testify to that 1,000,000,000-to-1 asymmetry. Physics did not simply prefer matter, it preferred it by the narrowest conceivable vote, leaving behind a cosmos rich in structure, yet sparse enough that light could travel, cool, and eventually give rise to questions like these. We have measured the fracture. CP violation is real, but the standard model's tiny bias cannot account for the vast architecture of galaxies. Somewhere beyond present energy frontiers lurk deeper breaks or altogether new symmetries that magnified the imbalance. Did supersymmetric particles tip the scales, only to hide beyond the reach of current colliders? Do neutrinos violate lepton number and whispered? Neutrinos decays deep underground? Could dark sector forces echo a symmetry we have yet to name, shaping invisible matter into halos that cradle every visible star? In the final segment, we will step back from molecules and galaxies to reflect on what this tapestry means. Why does a universe stitched from probabilities and partial patterns feel, at human scale, so solid and comprehensible? How do broken symmetries grant not only structure, but memory, music, and meaning? Join me for the outro, Harmony in the Imperfect, where we'll gather every thread. Noether's ledger, the sun's quantum heartbeat. the cracked mirrors of CP violation, and the snowflake melting in your palm to one final reflection on a cosmos forever poised between balance and becoming. Step back with me, far enough that continents blur into mottled greens and oceans into a single shimmering band. From this vantage, the entire planet is a snowflake of geology. Mountain ridges radiating like crystal arms, river deltas branching in mirrored pairs, hurricane spirals twinning in opposite hemispheres. Even here, symmetry whispers. Yet peer closer, and each valley deviates. Each cloud tilts a fraction off its counterpart. Those slivers of asymmetry keep rivers flowing, winds circling, life forever improvising new forms. Across our journey, we trace that balance from the mathematical to the tangible. Emmy Noether showed us that whenever the universe refuses to change under a certain motion, be it a slide through space or a tick of the clock, something precious must be conserved. That hidden bookkeeping steadies Earth in orbit, lets diamonds endure, and times every photon forged in the sun's core. Then we slipped inside that stellar furnace to watch quantum tunneling soften an otherwise impassable electrostatic wall. Proving that perfect rules can harbor humble loopholes, we saw the weak force crooked in its mirror. Turn protons into neutrons just rarely enough to stretch a star's lifetime across billions of dawns. We rolled time backward to a hot, symmetric embryo of a universe so uniform it almost erased itself only to witness symmetry snap in stages. Each fracture unlocking new layers of complexity. Mass from the Higgs field, matter's narrow victory over antimatter, density ripples that would one day blossom into galaxies. Closer to home, we wandered through snowfields, silicon wafers, and single sheets of graphene, noting how translational order and rotational elegance guide electrons, bend light, and carve ice. Along the way, symmetry's missteps proved as vital as its rules. Broken mirror laws color butterfly wings, twisted graphene angles birth superconductivity, and a chiral bias in amino acids lets proteins fold with purpose. Beauty, it seems, is born where order meets deviation, where the universe keeps its promises, yet allows a margin for creativity. Perhaps that is why humans find symmetry comforting but perfection dull. Our brains are wired to recognize pattern, yet our hearts quicken at the unexpected flourish. A syncopated rhythm, a tilted facade, a comet that refuses a circular path. We are children of fractures. Every atom in our bodies survived a 1,000,000,000-to-1 matter bias. Every breath depends on weak force irreverence. Every thought rests on electrochemical pulses choreographed by quantum statistics. So the next time frost paints your window, remember the celestial genealogy of those delicate hexagons. Recall that a hydrogen bond's 120-degree embrace echoes. It's the same geometry that lets carbon weave graphene and Saturn sport its icy rings. And know that without the tiniest departures from symmetry, without the gift of imperfection, there would be no rings. No ringside observers, no stories to tell. This is cosmic canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.